Section 2.6, we're going to jump back into Chapter 2, which was about derivatives. It's just a really nice kind of culminating review piece that hits on some of the things we did in that section, takes things a little bit further, that's true, but it does a lot of really nice review pieces. And it also makes Chapter 2 more manageable on a single test without this section in it from before. So when we do get to the final, you will see one question related to 2.6, and you will see one question related to 3.7. That will happen, okay? Whereas I'm not necessarily going to guarantee you that there's going to be a question from section 3.1. There may be, there may not be. It's a little bit less like that because you've already been tested on those and you won't have ever been tested on 2.6 and 3.7. So related rates is our section here. And we're going to talk first about the guidelines for solving a related rate problem. So often there is a simple sketch that you can make that will be helpful. I'm not grading on your accuracy of your sketch, that's not the point, but it helps us sometimes to visualize things by drawing them. The second one is to set up an equation relating all of the relevant quantities from your sketch, typically speaking, right? Step 3 is the part where it's going to look like something you've seen before, but also look a little different. We're going to implicitly differentiate. So we're going to do an implicit differentiation of both sides. The part that's different is that it's going to be with respect to time. Before we were doing implicit differentiation with respect to x and y. So that was different, right? We were working with x and y only. We're going to be working with time on this one. You'll see how that looks when we do one. Step 4 is to substitute in values for all known quantities and derivatives. So known quantities, known derivatives. And then step 5 is to solve for the remaining rate. So the types of problems we're going to be working with in this section are going to be like word problems. They're not going to be just here's a formula, do something, right? We're going to be creating the equation. We're going to be creating the image that associates with the description that we are giving. We're working with word problems or application problems. So we're going to take a look at an application problem to start with that has a very simple image, but you have to make sure you understand what the description is to be able to draw it properly. So it says a fish is reeled in at a rate of 1 feet per second from a point 10 feet above the water. So we can actually pause there and we could draw a little bit of what it's just talking about. It's talking about there being water, and they're talking about there being a 10-foot vertical, right, that the fishing line is being used from. So up here is my person with the fishing line. Okay, I'm not finished with my picture, but this is what I've read so far. Okay, I haven't dealt with the 1 feet per second. We'll come back to that one. But this is my image. The fish, there's a fishing line out there, and it's 10 feet above the water that it's being reeled in at, and there's the water below. It wants to know at what rate the angle of elevation between the line and the water is changing. So I'm going to draw my fishing line in as well. So if you can imagine if somebody throws out a fishing line, initially it looks like some sort of an arch, right? But as you start reeling it in, what you end up with is you end up with an image that looks something like this. And this fishing line's getting closer like this, right? Through the water, right? The fish does not come up out of the water and then get reeled in. It stays in the water getting reeled in. So the fishing line gets shorter because the distance is changing at this diagonal kind of a distance, right? So these are getting closer. Eventually it gets close enough that it comes straight up that sort of black piece that's vertical. Okay, so everybody have a picture of what's going on? Okay, I'm going to simplify my picture and only include one of these lines because I only need one of them to describe what's going on with my angle that it talks about. It says, what is the angle of, talks about the angle of elevation between the fishing line and the water. So the fishing line is this sort of grayish diagonal piece one that I did, and the water is in blue. So the angle it's talking about is down here. It's also worth mentioning that that phrase angle of elevation actually means that you go from a horizontal and you go up. So you can see that our horizontal is the water and going up is along the fishing line. So angle of elevation descriptively makes sense that it's right there. What shape did I draw? It's a triangle, and we know lots of things about triangles. So let's talk about what we know about triangles. You probably know the Pythagorean theorem, right? A squared plus b squared equals c squared. You probably know SOHCAHTOA, right? Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we don't necessarily know what of those pieces we are going to need, but we know a lot about triangles. If this talked about area, which it's not, of course, we would know the area of a triangle, 1/2 base times height. Triangles are a very familiar object to us. All right, so let's take a look at the rest of the pieces of information. It says it wants to know what the rate of the angle of elevation is that's changing between the line and the water when there's 25 feet of line. So at some point, this is changing, right? This changes. But at some point, it's going to be 25 feet, right? That's the description they gave us. It's going to be 25 feet at some point. And it also talks about how things are changing. So this piece right here is getting shorter, right? So this one's getting shorter. And the rate at which it's changing, it says, is it's being reeled in at a rate of 1 foot per second. Do you see that up at the very top? So it's decreasing. It's getting shorter by 1 foot per second. And because it's getting shorter, we call that a negative 1 foot per second. That's a rate. A rate is how something's changing. It's changing. Its rate is changing by negative 1 foot per second. What it wants to know is it wants to know how the rate of the angle is changing. So let me draw one of those in again. I'll change the color this time. As this is changing right here, right, this would be an additional sort of a few seconds along. It becomes more like the orange line. And my angle comes over here, right? The angle got bigger, correct? Can you see that the angle is larger from the gray angle to the, or gray or black, whatever it was, to my orange angle? The angle is a bigger angle than it was before, right? This measurement right here is bigger than this measurement right here. So the angle is also changing, and that's what it's asking me to find. It says, at what rate is the angle of elevation changing? Those are the phrases up there. Well, that angle of elevation needs to have some relationship to these other things. There's one more piece that I didn't write in. I failed to do so. This is 10 feet. And it's never changing, right? The guy is standing on the dock, or the guy is standing on the shore, the guy is standing on the boat. Whatever he's standing on, that is a constant 10 feet above the water, according to the description here. He's not changing his height from the water. Okay, so I need something that relates those quantities. So what quantities am I referencing? Well, the 10, because it's going to be part of what I know, right? I know this 10. Something about this fishing line, because it's changing. And at some point I know it's 25. It's changing by this 1 foot per second. And this angle. So I need something that will relate my angle, my 10 feet, and my fishing line side. What's that going to be? Like, what relates those three quantities? Okay, the Pythagorean theorem would relate 3 of the sides. And I'm not relating 3 sides. I'm relating 2 sides and an angle.
It's
something in SOHCAHTOA, right? Yeah, so something in SOHCAHTOA. So it's either sine, cosine, or tangent. So we need to figure out from this angle what these 2 pieces are. So if I do the 10 feet, is it the opposite, the adjacent, or the hypotenuse?
opposite.
Opposite. This one's opposite. What about my fishing line over here?
It's hypotenuse.
That one's the hypotenuse. So which trig quantity relates the opposite and the hypotenuse?
Sine.
That would be sine. So sine is what I'm going to want to use. And do you see how helpful the picture is in making that decision? Because I'm going to tell you what, I would not be able to read this description, forget my picture, and be able to figure out that it was sine. I wouldn't be able to do it. I'm a very visual person anyway, so it makes sense to me that it would have to be. But I think it's a very big challenge to not draw a picture and to be able to get to the point that you're recognizing that this one in particular is sine of theta. So sine of theta, and I'll write it first the way we just described it, opposite over adjacent. and then we're going to write those pieces in. So what's the opposite? Well, it's the guaranteed 10 that never changes. Oh, I'm sorry. I just wrote it wrong. Thank you. Keep me straight. There we go. Opposite of hypotenuse. Okay. So the opposite 10 is the part that never changes. So that's for sure going to be 10. Now, at some point, the hypotenuse is 25, right? But not all the time, right? It's being reeled in. So I need a variable to represent the hypotenuse. What variable would you like to use? X. X it is. So this length right here is now going to be called X in general, and at some point, X is going to equal 25. Okay. So most of what we've done so far is really more like what you would have seen in a trig class. Like this image, being able to draw that, being able to find quantities with a trig function. The part where calculus is involved and what puts this into section 2.6 is that I need to find that rate, right? Those rates that are mentioned. In particular, this shorter piece right here, this rate, is how the variable x is changing with respect to time. Because it's changing as time changes, right? And this angle right here, I want to figure out how it is changing. Remember, these are ratios, d theta, with respect to time. So I'm going to have a dx and a d theta that I'm going to be using and or looking for in this problem. And I do that by doing implicit differentiation. Now, it's much more helpful if I write this as 10x to the negative 1. So we're going to do that. And we're going to take the derivative of both sides. So what is the derivative of sine of theta? Cosine of theta. Very good. But we're taking this with respect to time. So the derivative of theta is theta. Theta is a variable, and I need to do the derivative of theta with respect to time after I do it. So this is d theta dt. Because theta is changing, just like normally when we would have done implicit differentiation with y, anytime I took the derivative of y, I had to write dy dx. Y'all remember what I'm talking about? I hope so. That's what's going on here. Every time I take the derivative of theta, there will be a d theta dt. And every time I take the derivative of x, there's going to be a dx dt. So let's do the other side where that piece happens. So the 10 is going to stay. What's the derivative of x to the negative 1? Negative, and then x to the negative 2. Good. And then because this is with respect to time, I will get a dx dt. So every derivative I do is going to have d of whatever variable it is, dt. Are all going to have that. Okay. Now, some of these things we know. We'll change this and clean it up a little bit because it's kind of messy looking. Do I have a blank screen? I do. All right, so let's take this over here. And we'll clean it up just a bit. So this is cosine of theta, d theta dt. And it equals negative 10 over x squared dx dt. Okay. There's two of these pieces of information. There's three quantities here. Let me just mention that. I have theta, I have d theta dt, I have x, and I have dx dt. Do you see four different things that we actually have sort of as variable quantities here? Okay, good. So I need to have three of them filled in order to find the fourth. That's the way algebra works, right? We need to know all but one to find the last one we don't know. Can you tell which of these four you're needing to find? What is it asking you to find in this question? Which of those four quantities does it ask you to find? D theta dt. You got it. So this is the one it's asking you to find. It's highlighted second here. It says the angle of elevation theta is changing. What is that angle of elevation? What is that rate? Here's the word rate up here. At what rate? So I need to find d theta of dt. What that means is those other three, namely theta, x, and dx dt, must all be given to me or able for me to find in something that's a nice way. So can you tell any of those quantities that you know for sure from this description?
Isn't x 25?
X is 25, you bet. That's the point at which we're finding it, right? It's the exact point in time that we're looking for. So x is 25, very good. So I'm going to have, d theta dt here, that part I don't know, and I'm looking for. And I know x, it's 25, so 25 squared goes down here. There's one more that's very clearly given to us. Do you see it?
The rate.
Yeah.
Is 1 feet, that's negative 1 feet a second.
Yeah. Down here, the rate that the x is changing is given to us. It's negative 1 foot per second. So, whoops, this one over here then would be -1. Okay, theta is not given to us, right? I mean, it's just not. But can I figure out what theta would be at that given point in time? I can. So take a look at this. Here's this triangle here. Here's the theta I'm looking for. This one's always 10. And at the point in time where I care, the angle, or the hypotenuse, is 25. I should be able to figure out what theta is. What relates theta, 10, and 25 again? Sine. Yeah. So I can set up an equation, sine of theta, and it's going to be equal to 10 over 25 at this one moment in time. And I can find the theta then that corresponds to that. Do you remember how you do that? And you do need some support. Yeah, good job, Caleb. Inverse sine of 10 over 25, and it will be an ugly decimal, and your calculator will be necessary. Just because it's giving you a value, 10 over 25, that happens to look kind of nice. I mean, like it simplifies to 2/5. 2/5 isn't like a unit circle value or something, so it doesn't really help me that it simplifies to 2/5. So if you do inverse sine of 10 over 25, remember we're working in radians. What do you get for this angle measure? Let's go with 4 decimals. We want to keep several decimals. I think 4 is enough, so. Okay, so my theta is 0.4115. So over here, I can put in 0.4115 for theta. Now there's only one thing that's unknown, right? The piece I'm looking for. And I should be able to simplify everything else. Your calculator can be a good support with this. Some of those things you might want to just do by hand because it's easier than even putting it into your calculator. For example, I don't think you need to put in 2 negatives over here on the right-hand side. And you probably know that 25 is 25 squared is, and if you don't, that's fine. But that is the quantity. And then your cosine of 0.4115. We would move it to the other side. So whatever that is, it gets divided to this other side. And your d theta dt will be the result. Our answer is going to be written to 4 decimal places. It'll tell you how many decimal places inside of WebAssign, and I'll tell you on the final when you get there or on your quiz if you need that information. What do you get when you take 10 over 625, and then you divide it by cosine of 0.4115? It's going to be positive, right? Because the angle's getting bigger. It's small. Anybody get a calculator answer yet? I have 0.0175. Did anybody's calculator tell them that? Yeah? Okay. Thank you, John. I appreciate it. This is a word problem. It's an application problem. It's going to have units. So what are the units? Well, remember this is a rate of change. So take a look at where things are here. What are the units on theta? Radians. We're measuring theta in radians, right? So I'm going to have radians. What are the units on time? Seconds. So this will be radians per second. You can write it in words, you can write it in a fractional form. Either way, that would be our units. Okay? If you're going to be dealing with a triangle, I expect you to know pieces about a triangle, right? You should know enough about triangles to not need anything additional. Number 2 is a little different. Number 2 requires an image that you might not remember some details about. It's a spherical balloon, so you may or may not remember details about a sphere. It says it's being inflated with gas at a rate of 800 cubic centimeters per minute, and it wants to know how fast the radius of the balloon is increasing when the radius is 30 centimeters. So you probably have a picture in mind of a balloon. And it would look something like this. And we're blowing the balloon up, right? With an air pump, with, our mouth, whatever. We're increasing the size of the balloon. This is talking about cubic centimeters. Cubic means you're working with a volume. I would expect that you would remember that piece, but you might not remember the volume of a sphere. For those of you who came to Math Club, that actually came up with a surface area of a sphere came up in one of the Math Jeopardy questions. But does anybody remember the volume of a sphere? Just happen to. It's not got a 2. It's okay. It's 4/3 r cubed. Pi r cubed. I missed a pi. Sorry. Moving too quick. 4/3 pi r cubed. There we go. That is the volume of a sphere, which was an incorrect answer by one of the teams when it was asked for surface area, actually. All right, so this is what we're going to be taking a derivative of, is because this is the quantity that relates the balloon, right, how the balloon's being inflated with gas, and the radius, which is what the other reference point is, or question part in the question. The other value that's referenced in the question. There we go. So we're going to be taking the derivative of this. There are some pieces of information. At some point, it tells us that the radius is 30, right? Specifically 30 centimeters. And it also tells us that the rate at which the inflation is happening, the one that's highlighted there, it says cubic centimeters per minute. That's what this would look like, cubic centimeters per minute. That's how the volume is changing. So this is dV dt. The volume is changing by cubic centimeters per minute, and in particular, that number is 800. And it asks us for how fast the radius is changing, which means that it wants to know how the radius is changing with respect to time. This is the thing I don't know, and it's the thing I'm asked to find. So we're going to take v equals 4/3 pi r cubed and take the derivative. The derivative of v is just dv dt, so that one's very nice. 4/3 comes along for the ride, as does pi. What's the derivative of r cubed?
Well, 3r.
Yeah, 3r squared. And then every time I have a variable I'm taking a derivative of, I'm going to write d of that variable, so this is dr, and then dt. Unlike the last one, which had 4 pieces of information, this one only has 3 quantities that are unknown. dv dt, or that are variable anyway, dv dt, r, and dr dt. And 2 of them we know, they're written down here at the bottom, right? So dv dt is 800, so I'm going to put in 800 on the left. I do not put units in the middle of these problems. I think it makes them look really messy and confusing, and I don't need them until the end anyway, so I'll put them back on at the end when I need them. We have our 4/3 pi r cubed, 4/3 pi times 3r squared. Notice that these 3's would cancel, so I'm going to go ahead and do that so I don't have to write them. I have 4 pi, and then I have r. R is 30, so it's 30 squared. And then I will be able to find dr dt. Because it's the only thing that's not known then, right? The only variable quantity at this point is dr dt. So if we would divide both sides, we can multiply this out. 30 squared would be 900. 900 times 4 is 3,600. So let me actually write that. So this is 3,600 pi. 800 on the left, dr dt. And then I can divide by that 3,600 pi. Notice everything we're doing here sort of defies some of the properties and rules of things I've said all along, which is keep things exact. We're not keeping things exact here, and there's a very good reason. This is an application problem. If you go telling somebody that the rate of change is 800 over 3,600 pi, they're going to look at you like you're nuts, right? Those of you who are going into engineering or physics, that would be a crazy way to answer somebody's question about an application problem. What they need in order to make sense of it is some sort of a decimal approximation. That's why we're doing it. And if we take this division and we do this, we get 0.070 with 4 decimals, 0.7. Units on R is centimeters, and then units on time on this one is minutes. So this is centimeters per minute. All right, so I will post a video. It will be short for the number 3. And I'll just post it separately so that you can watch that separately and don't have to pick up in the middle of this one. It'll be a video that I've recorded probably last semester. I don't know. I'll find one that has it in there nicely, and I'll post that part of it, all right?